Great. Masi set me up with his last slide, or second to last slide, about accuracy requirements. And a couple other people so far have talked about accuracy requirements. So we're going to be talking about eigenresidual tolerances for spectral partitioning. This is a very concrete analysis for a specific problem, but I think is part of a bigger movement to understand how accurately we need to solve these problems to do data mining on graphs. So if my slides advance properly, they do. Okay, so graph partitioning, which is also related to spectral clustering, is you're given a graph, nodes and edges. The nodes come in these groups where they are more densely connected to each other, to their co-group members, than they are to the members of the other groups. You don't know the groups a priori, but the goal is to find them. So here in this graph that's drawn, you see four groups going around. They're about the same size, and you can see the dense connections inside and the sparse connections between them. So we're going to go through linear algebra to get there. The goal is to start from a graph and recover this partition, or this clustering. For social networks, this is called community detection. We're all trying to do the same thing, which is find groups of vertices that are more related to each other than they are to the other people. So we go through linear algebra, the adjacency matrix, one entry ij if vertex I is connected to vertex j. Everyone's talked about this today. The degree matrix. We're going to focus on the normalized Laplacian, I minus d square root inverse a d square root inverse, and the normalized adjacency as well. So some basic terms of numerical accuracy is just start with the eigenproblem, LV equals lambda v. All the eigenvalues are positive for the Laplacian, or not negative. The Rayleigh quotient mu, eigenresidual r, and the error. So eigenresidual is measuring how close you are to solving the eigenvector problem. The error is how close your vector is to the closest eigenvector associated with the eigenvalue you're looking for. And then our data mining problem is to minimize conductance. So the conductance is how we're going to measure how good our partition is. If conductance is small, then that's a good partition. If it's large, then that's a bad partition. And it's the number of edges leaving your set S. S is a set of vertices. So the number of edges leaving the set S divided by the total number of edges within the set S. And the point of this work is to understand how you've started with a data mining problem, say minimize conductance. You've transformed it into a numerical linear algebra problem, compute eigenvectors. We want to know how accurately do I have to compute those eigenvectors in order to solve my data analysis problem. How accurately do I have to do it to get the clusters? So here's kind of the algorithm we're going to go through to do that. You approximate an eigenvector of L so that the residual, Lx minus mu x, is less than epsilon. Epsilon is the residual tolerance here. And then you sort that vector after rescaling it by the degrees. And you check all possible cuts. So once you've got an ordering on the vertices, there's only n possible cuts that are consistent with that ordering, and you pick the best one. So that's easy. What we care about is how do I choose epsilon small enough that I get the right answer, but large enough that I'm not spending too much time working on the problem. That's what we'll do. So the reason why these two things are related, conductance and eigenvectors, is through the Cheeger's inequality, which is just saying that if you have a vector orthogonal to the kernel of the Laplacian, then, and its Rayleigh quotient is mu, then the best sweep cut of that vector has conductance less than square root 2 mu. People usually state this in terms of x being the second smallest, the eigenvector associated with the second smallest eigenvalue, which is called the Fiedler vector, but it is true in this more general setting. So what this tells us is that it's sufficient to find low energy vectors with respect to the Laplacian. Eigenvectors don't really matter, other than they're a convenient way to find these vectors. So that's what we're going to do. So there's some error analysis here. On the left, we're summarizing the Cato-Temple inequality, which is saying that if you're trying to compute an approximation to the Fiedler vector, you measure your error in the 2 norm as the distance between the vector you have, x, and the vector you're trying to compute, v2. So the error is the distance between the vector you have and its projection onto the Fiedler vector. Then the relevant quantity of interest is the eigengap, lambda 2 minus lambda 3, and the error is less than, or sorry, error times eigengap is less than the residual. So that's saying, that's how we relate. I can measure the residual, and my solver has told me that the residual is small. I also know that the error is small. When the eigengap is small, my guarantee is not very helpful because it says the error could be bigger than the residual. But that's the bound we're going to use. And it has this condition that the Rayleigh quotient mu has to be less than the midpoint of the second and third eigenvalue. So we generalize this to computing elements of invariant subspaces. So you're just trying to compute any linear combination of the eigenvectors associated with the, okay. Trying to compute any linear combination of eigenvectors with the q smallest eigenvalues. This is a much bigger set of things that you're trying to compute, but you just need one linear combination. And you measure the error in a similar way, the L2 distance between you and, or the vector you have and its projection onto the space spanned by the eigenvectors of interest. And you get a similar bound. So error times gap is less than residual. And the gap here, instead of being the difference between 2 eigenvalues that are adjacent in the spectrum, it's the difference between the Rayleigh quotient you have and the first eigenvalue outside the interval that you consider acceptable. So the way you use this improvement to the Cato-Temple inequality is you say, I've analyzed my problem to come up with a set of eigenvectors that are sufficient to solve the problem. That gives me a range of eigenvalues that are considered the good eigenvalues. And I'll take any linear combination. So my error bound is much better here in terms of residual. So I can, that's it. So yeah, you analyze a problem to find a set of good eigenvectors, as in they solve your data mining problem. And what you end up giving up is control over which linear combination you get. You're going to get any arbitrary linear combination, but what you gain is tighter error bounds and faster convergence. So we're going to work this. We're going to work an example here. So this relates to spectral partitioning because if we can take a graph, so we can take a graph. We know that the eigenvectors associated with the small eigenvalues, any linear combination of those eigenvectors is going to give me a good partition. So that's my target space. So I'm going to compute one of those and show that the residual tolerance I need is much bigger than if I'm trying to compute the Fiedler vector. So we're going to work out an example. Here the graph shown on the left is the ring of cliques. It's been used for analysis in many problems, particularly modularity, which is another community detection framework. So we like this graph because the community assignment is unambiguous. The cliques, so the fully connected subgraphs, they are the communities, the clusters, and the spectrum is easy to compute on pencil and paper because of the symmetry. So this graph has q cliques, each of size b, and they're arranged in a ring. That's why I call it the ring of cliques. And then the drawing on the right is the adjacency matrix. So you can see from the adjacency matrix it's got a lot of structure, and that allows us to figure out what the eigenvectors are. So the optimal partition of this graph is to assign all the vertices on the left to one part, and all the vertices on the right to another part. And there's the 2D symmetry, but kind of half the circle on one side and the other half the circle on the other side. But if you're just trying to recover the clusters, you're going to do something like recursive bipartitioning. So you're going to cut the graph in half, then you're going to take each half, cut those in half, until you get down to the smallest size you want. And in that case, all you need is that all the vertices in the same clique show up on the same side of the partition. So you can assign the red and blue arbitrarily in this fashion. As long as everybody in the same clique gets the same color, we're good. So that's how we get from the Fiedler vector to a larger set of vectors that solve our problem. So if we look at the spectrum, what we see, now this is in the normalized adjacency matrix A, so eigenvalues close to 1 are good for partitioning, and eigenvalues close to -1 are bad for partitioning. So here, you see a clump of eigenvalues up near 1, then this huge gap, and a bunch of eigenvalues close to 0 and negative. So what this is saying is the spectral gap is going to be small. In fact, it's 1 over n squared, where n is the total number of vertices. But this blend gap, this mu minus q plus lambda q plus 1, is constant if you choose q to be the number of cliques. So that's important. And if you look at the eigenvectors themselves, what you see is they're block constant and periodic, going around the circle. So if you take block constant vectors and add them together, you get more block constant vectors. So that's how we know that any linear combination of the first q eigenvectors solves the problem correctly. And yeah, the eigenvalues correspond to the frequency around the circle. So then what we need to do is show, okay. So we've identified a subset of the spectrum that correctly solves our data analysis problem. We've identified what the relevant gaps are. Now we need to figure out what's the error that we need, or the error that we can tolerate and still get the right answer. So here we go with a construction, or a constructive proof of what that error is. If you take your approximate eigenvector, x, and you sort it, what you end up with are these blocks. And suppose you have an element of the first q vectors. Then all the vertices in the same clique got the same value. So anywhere you cut, you're going to get the correct labeling. But we're going to perturb this in the smallest possible way. So we take each block, and like all the values have the same, all the vertices have the same value, except for one, which we're going to push up. And then we're going to go to the next block, and we're going to push the first vertex down so that it crosses the value we gave to the previous vertex that went up, right? And then keep going so that there's no possible threshold to make your sweep cut. There's nowhere you can draw a threshold and say, everybody below this value, you're on the left. Everybody above this value, you're on the right. Anywhere you try to draw that threshold, you'll make a mistake. Some vertex will be estranged from his community. And the point here, like this is a minimal construction, and we can bound the norm of that construction. So what you end up with is getting 1 over the square root of q times n as the error that perturbation induces. So if you have any vector that is, so it's error to this blend space is what we call it, with the span of the first q eigenvectors. So you have any vector whose distance to this space is less than 1 over square root qn, you know that that vector correctly identifies the clusters. And then if you come up with an upper bound on that, you say, what is the norm of that perturbation? You get 1 over square root b. So this is possibly not tight, but that gives you a, so from the previous slide, we know that if I've solved to an accuracy less than this amount, I will correctly identify the clusters. From here, we know that there is a perturbation of this amount where I will make a mistake. And those are separated, but that's kind of what you want. So you want to know an error at which, if I've solved to this error, I'm guaranteed to be correct, and this other half. So you plug in various values of Q and B, and it turns out that the sufficient and necessary accuracy match for the Q is a constant case. So if the number of cliques, or the number of clusters is constant, and the size of the clusters is growing, then you end up with these two match at 1 over square root n. So we checked empirically that those formulas hold based on doing numerical simulation and making the perturbation. And then from this argument of we know what the necessary accuracy is. Okay, I'm ahead of schedule. So based on this argument of we know what the necessary accuracy is and we know what the relevant gaps in the spectrum are, we're able to show that the power method converges in log base b of q steps. So what this is saying is if you're just trying to find the clusters, you can be done very, very rapidly. But if you want to find the optimal clusters, so that those two halves, the left half and the right half, you need to solve to much higher accuracy, or use many more iterations. And here, actually, log base b of q is a really small function of b and q. So the conclusions are that I'll just slow down, wax poetically on the conclusions. So yeah, by reframing the problem from computing the Fiedler vector to any low energy Laplacian vector, we're able to understand the accuracy requirements and show that the accuracy requirements in terms of residual tolerance are much lower. And then we're able, for this particular problem, we're able to show that if you're trying to recover the Fiedler partition, which for the ring of cliques is the optimal graph partition, over all possible partitions, not just spectral partitions. Yeah.
So when you say lower accuracy, means larger tolerance?
Yes. Yes. Low accuracy means larger tolerance. So if I'm going to take a drink with all of my luxurious time. It's very dry up here. So, right, for this problem, we're able to compute the residual tolerance necessary to find the Fiedler partition, and also the residual tolerance necessary to solve the data mining problem, to recover the clusters. And we show a huge gap between those. So if you're trying to do spectral clustering or spectral partitioning and get the optimal spectral partition, you need a very small tolerance. For this problem, n to the negative 5 halves. But if you just want to find, in this case, if you're trying to recover just the clusters, the data mining information you care about, then 1 over square root n is sufficient for residual tolerance. So this answers Austin's question that he asked me in October at a different conference. This is how you set Eigs, the tolerance you're going to give Eigs. It's 1 over square root n, unless you really care about getting the right answer, in which case you're kind of out of luck, because for moderately small problems, or moderately large problems, n to the negative 5 halves is infeasible. So what else do we learn? Oh yeah, I really like to encourage people to work on model problems that either they invent or they find in other people's papers, where they're able to understand the spectrum of their graph in a lot of detail. Because then you can really get at what are my accuracy requirements for solving this data mining problem that I care about. So in ranking, this is another big task. Everyone does the experiment where they rank and they look at the tops of the lists and the top of the list matches, and then they're like, oh, I don't need that much accuracy. But we don't really know what the accuracy requirements are, and we don't know how the accuracy of the ranking depends on the accuracy of the solver. And I think the only way to get really clear understanding of that is to go through these model problems, like the ring of cliques. Obviously, the more model problems we have, where people understand the spectrum, the easier it will be in the future for people to use model problems. And then, yeah, if you're solving a data analysis problem by using linear algebra, the data analysis information can be recovered much faster than accurate solutions to the linear algebra problem. That's all I've got, but I'm happy to take questions for a long time.
So we still have enough time to grill James mercilessly. So
Yeah.
I'll start. Right back there. Hit his hand up quicker.
So you kept saying the optimal feeder partition.
Mhm.
Is that just like, that's only optimal for this specific example? Usually it's like, the feeder partition is just an approximation.
Right. So one of the reasons we like this problem is that the Fiedler vector gives you the optimal partition of the graph. Yeah, so that's the part where you have to analyze your application to understand what part of the spectrum you actually need. Here we're able to say, we're doing spectral, we're doing bipartitioning recursively, so that tells us what we care about is when we get to the leaves of the recursion tree, all of the cliques are preserved, because then we've learned the information we're trying to learn. So here, all you care about is all the cliques are preserved on each side of the cut, and that at least one clique is on the opposite side of the rest of them. But go ahead.
And then Eric.
So you're assuming that a thorough understanding of model problems will shed light on real world problems.
Yeah.
To me, that is a leap of faith. How do you justify
Yeah.
this question?
Okay. So the question is about, isn't it a leap of faith to go from model problems to real world problems? And these results, any result you get on a model problem do not directly bear on the real world problem. But it's very hard to understand why things are happening the way they are in the real world problems. There's so much going on, degree heterogeneity, complex structure, all of it, that you can't really, it's hard to do pencil and paper analysis on real world graphs, whereas in model problems it's easy. And then I have other work.
This is like the guy who's dropped the keys and at night and looks for them under the lamp post, right? Because that's what like.
Oh, yeah.
So you need to give some justification.
Yeah, so this work has kind of corresponding work on real world problems where we don't know what the spectrum is a priori, but we use insights from this to determine stopping criteria for real world graphs.
Let's go to Eric.
Go ahead.
So I'm not so sure that the feature of vector is an optimal solution to the partitioning problem, because partition problem is a discrete NP-hard problem. The feature vector is just the solution of the relaxation, the continuous relaxation.
Yeah. So it happens for this graph, the solution to the continuous relaxation is the solution to the discrete problem.
You're not trying to this is
No, yeah, right. Yeah. So that's why we like this model problem. Because you're able to say, if I've solved if I've computed the Fiedler vector exactly, I'm guaranteed to have the best partition of the graph. I'm also guaranteed to recover, if I do bisection, I'm guaranteed to find the right leaves of the recursion are right.